Okay, so here we are. Welcome to the first in a series of three, well, four actually, machine learning kind of overview presentations, lectures. So let's jump into the first one. I apologize if I kind of cough along the way here. Still fighting through a little bit of a cold. So here are the themes for this. We're going to talk about the machine learning lifecycle, even though we've done that a little bit. What are the conditions that are necessary for machine learning, and then just like general kind of machine learning terms and phrases. All right, you'll see that we got this broken down into three sections. So each week we'll go through a new section of this as we work through um, kind of each one of the introductory components of machine learning. But we're going to do it based off the phases that we have there, and then at the very end we're going to do a section just on evaluation because it's pretty important. Okay, so let's keep going here. All right. So I'm trying to get me out of the way. Let me over here, maybe zoom this in just a bit. Whoa, too much. All right, use my fingers. Better mechanism. Okay. All right. So first off, this 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 data science lifecycle down here is kind of a cartoonish version of the one that I'll present that I showed you guys already. This is kind of the lifecycle associated with software development, all right? And this is important because I just want to show you the difference between the two. We're going to get into what is machine learning and all these things. But I think just this overview right at the front about what a data science or machine learning lifecycle kind of looks like is instructive. All right, so the important part here, and I'll just key in on this just for brevity purposes, is that much of what we think about when we're doing software development, when we do construction and development of the actual software product, it's all done in-house, right? So we do a lot of dedicated work in this kind of third step here, right? That's why I kind of circled it twice. And then when it goes into release, you definitely maintain it, right? Your bug checking, you're ensuring that the various components are doing the things that you want to do. But in large part, if you're rigorous in this step, right, what you hope is that nothing changes here in the outcome. Right, the difference between that process and what we think about in the data science lifecycle is that much of what happens in the world of data science is totally unknown, right? Until we actually put our models into deployment. So that's a big difference. Certainly, all of these things here are going to be, very, very important. All the stuff here on the back end, all right? But in all honesty, we don't going to know a whole lot about what happens to our models until we actually put them out into the world. All right, so this is a pretty big difference, all right? And actually foregrounds kind of everything that we think about when we think about machine learning, because much of what we're going to talk about is like, what are the conditions that work for machine learning? Do we have a really good question? How do we track the metrics? What are the risks associated with it? All right, all of this is calibrated. And the reason these components are so important is because of this divergence in between these two concepts, all right? We don't necessarily, we build our data science products in-house, but we don't really know how much utility they're going to provide us until we put them out into the world. And because of that, we have to be very specific about what questions we're asking, how we know it's working, how we track these metrics, right? And then what are the risks that we can take, right, associated with how well this model works to answer our question. All this is done in drift analysis, model monitoring. All of these processes are very specific, and they're all derived based off what we've done kind of up here about how well we understand our models, right? Kind of on the front end. Make this a little bit darker, I think. So with that, all right, let's move down into my version of the life cycle. All right, re-emphasizing the point here that everything that we know about our models can be certainly created inside where we're developing them. We won't really be able to validate it until we go out. All right, so we have basically these four phases. I know I've shown this to you before. All right, but we're going to talk about data science. We're talking about machine learning in the context of these four phases. In particular, the first three. All right, because that much of the class kind of focuses on these first three. We have other classes that focus more on this, all right? But what we're going to talk about is kind of through these first three phases of deployment. And also, it's just hard to get to all of these. So we're going to focus on the first three, all right? And the machine learning overview is going to cover kind of the nature of the things you need to know in the context of those first three phases, all right? Those being idea development, data prep and problem exploration, and then problem solution, all right? And then in this week's This week's class, we're going to focus on idea development. It could be a series of questions you should be asking every time you're presented with a data science or machine learning in particular problem, all right? And it's a subset of the potential questions you should ask. All right, so now what is machine learning? All right, so let's get into it. All right, let's talk about what is machine learning and how it's used. Again, I apologize, still a little sick here. All right, so these are some famous quotes, all right, from very well-known computer scientists or founders of the machine learning field, Mitchell, Goodfellow, and Samuel. You can read these to yourselves, but in general, I think the first one probably spells it out probably the best. It just gives the computers an ability to learn without explicitly being programmed, right? Being told exactly what to do. All right. The quote down on the bottom, all right, is sort more kind of a technical way to look at it in terms of just the experience and the sets of tasks and then the outcomes, right? It can actually be kind of mathematically defined through these different parameters, all right? All right, but the idea is that we give it a general set of constraints, all right? And then the machine learns patterns. This is what Goodfellow is talking about here. Learns the patterns inside the data given these constraints, and then generalizes the results onto new data, onto data it has not been seen, all right? And we'll talk through a lot of these, all right, as we get into this portion of the class, all right? So machine versus human, there's a whole list of things that humans are really good at and machines are really good at. I think these are kind of obvious on their face, all right? Calculations, repetitive tasks, defined rules, all right? Computers are very good at that, okay? We define what those are, and we give them to them so they can be automated, right? We're much better at understanding context, thinking through problems, asking the right questions, setting tools, and then most importantly, interpreting the results, okay? And there's a reason that it kind of goes like this, all right, over here. So think about this is all the context with which we'll be doing in that first phase, all right? We'll be understanding the context. We're going to read through a case study this week. You're going to have to understand the context of this marketing firm you're going to be looking at. And then you're going to think through a problem. You're going to ask the right questions. You're going to potentially select tools, all right? But then once all that is done, right, then you can move over to kind of the machine-oriented processes and let them take over. But then at the end, right, when you have the results, they still have to be interpreted back into all of this context, all right? No solutions live in a vacuum. If you fully automate your processes and just give it over to the machine learning or AI tools, it's just a matter of time before that starts to fail, okay? Especially when, the risk is certainly higher. It's always better to have humans in the loop. And this is why this important bullet here is kind of segmented down at the end, because it's almost like a process, right? But we have to remember that humans are usually the ones that putting the problem back together. Computers are really good at breaking it apart. We're better at interpreting the results, okay? So this is where we kind of live in the machine learning world in this area here. All right, so let's take a look at this is like a, kind of a genealogy, I guess. A way to look at it is a classical machine learning, kind of subclasses of different models. Right? So now we're getting very specific into the models. I mean, there's another set right here. It might be like semi-supervised or reinforcement, but generally we have two really broad categories: supervised and unsupervised. Right? The difference between these is very simple. Supervised has labels. We know where the data comes from and we know what the target classes are, and unsupervised does not. All right? And we're going to talk about this in a little bit more detail here as I get into some examples. But that's it. I mean, this is just categorized, all right? And this is not, all right? Much of the advancements when we think of like in AI systems or advances in technology all come from labeled data, right? So you have armies of interns somewhere labeling it, whether it's a dog or a hot dog somewhere, right? And we pass all those images in, and a machine knows it. Or you think the same for IBM or the Deep Blue or the other really famous kind of AI machines that you think of, right? They all learn to play these board games that all have very labeled data, all right? So the images, the different patterns and potential ways that the board pieces or the chess pieces or the Go pieces can lay is all defined, right? So that can all be learned in a very structured way, all right? As compared to unlabeled data, we're still a very exciting area of machine learning, but there's less progress been made here generally when we think about kind of the advances of AI, right? And here's just we don't have labels, right? It might be that it's a whole block of text or a whole bunch of images that aren't labeled, right? Or a whole bunch of numbers that don't necessarily have well-defined patterns. All right, and then what was the responsibility of the machines is to identify those patterns, right? To put the patterns in there, to put these things into more readable and understandable ways and learn a model around that, okay? Whereas one might not be present. Okay, here we'll have these very easy, on this side, kind of easy to predict. Think about your rows and columns like that, and this would be much less structured, all right? So let's put this into context, right? So if here we're talking about pattern discovery, right, for supervised, that's when we know, right, the inputs and the outputs are well known, all right? So we know a certain voter and that they're going to be affiliated with one particular, right, party or not, right? So we know what those labels are, right? Does this voter might be a Republican or a Democrat, right? So we know what those particular affiliation is. Unsupervised would be that we do not know what this particular voter is. We just have characteristics of this particular person, right? But we don't know whether they're going to be a Republican or a Democrat, right? And we would try and predict that, right? It's to be discovered. Or the other thing would be like we wouldn't even know how many parties exist, right? We just wouldn't have that information. Like, is there a way that we can model voter behavior, right, in certain groups, right? Assuming that we wouldn't even know that there were Republicans or Democrats. So that would be the difference. So here we would just have a block of kind of characteristics where we were not sure what they would map to, but up there we would know, that they were just these kind of two-party affiliations, right? This is just a little more detailed kind of genealogy, the same thing that we saw previously with supervised and unsupervised. Unsupervised is certainly broader than clustering, so that's a little misleading, but there are many different ways you can think of any of. Basically, all of text analysis is out here too, so there's lots of broader categories. We're going to spend most of our semester here in supervised. We are going to do k-means, so we're going to go through that later in the semester, right? Where we're not going to have labels. We're going to try and do some clustering, but for the most part, we're going to stay in supervised and in classification. All right, so I'll show you some examples of regression. And this is also a bit misleading because ensembles and decision trees could do both classification or regression. All right, but we'll get into that in a little bit more detail. But these are just some examples of how general models fall into kind of these broad categories. All right. So machine learning is a general use technology. What does this mean? All right, let's think about this. So general use technology, or a GDP, is a term, is a method that is invented that has enough protected aggregate impact across an economy to be able to be used in many different domains, right? So you think about this from kind of the examples that we talked about. I'm just going to pause here for a second. Sorry about that. I had to cough. All right. So when you think about the original examples that we did the first day of class, right, when we were trying to, take a look at data science job postings, they were all over the place, right? I don't have to reinforce this. You guys get it. Well, that's what we mean by that. That's the reason that data science, and in particular machine learning in this example, are so common, right, across all of these different professions, right? Because it's a general use technology. It can be used across a whole bunch of different industries, right? So we think about, and maybe this is, given the context of this class, you don't have to be told this, but the data is growing at just a ridiculous rate, kind of continuously. All right. So if you click on this, I don't know I have these slides in the Colab, so you should be able to click on this. Apparently I can't click on this. Maybe I can. Anyway, if you use this link, it'll show kind of it'll show the by minute kind of utility use of Twitter data. I'll pull it up here. I'm sure I can pull it up on this side. Hold on one second for me. All right. There we go. Let's pull this up. So here we're seeing, this is just a tweet sent just today, pushing 550,000, and this is tweets per day, so needless to say, anyway, it's just kind of a fun stat there. Pull it up and you see where you're at on your end when you click on that. But growing data availability at a crazy level. Error rates in ImageNet, if you're unfamiliar with ImageNet, it's just a big set of images. And errors mean that the models that are being built to terms of classify the images there, it's down from 30% in 2010 to less than 3% today, which is a big deal because anything less than 5%, I'll put a question there and I'll let you guys think about it just for a minute. Anyway, I'll just give it away. is less than human error. So the average human error on these classification tests is about 5%. So that means that the CNNs are doing well. Anyway, the models, the neural networks, I'm sure, that are being developed there are doing better than humans. But we also have to say to ourselves, okay, well, Deep Blue, that IBM AI machine, searched 200 million potential chess positions, all right, per second, and whereas Kasparov was able to do no more than 5 to 10, maybe per second, per couple of seconds. Yet he almost played at the same level, right? There was even a point where I think they were at a draw. He did eventually lose. So why is that, right? Why do we think that's the case? All right. So we think about these things as we go into kind of a machine learning overview, all right? And that one particular example will be important later. So before we turn everything over to the robots, we're really far away from what we consider a general intelligence, right, as compared to humans. And machines cannot do anywhere close to a full range of tasks that humans could do. Maybe we all know that, all right? But there are conditions as a result of this that are suitable for machine learning, all right? So we call this SML, all right? So understanding machine learning, I think, is important to understand these conditions which need to be present for it to work. It's not a panacea. There are some things that work really well and some things that in some conditions where it doesn't. So let's take a look at these. All right. So the important thing about machine learning, right, requires a very detailed level of specifications, right? What needs to be learned and data to support that, right? This includes engineering features through a series of trial and error, right? It has to be kind of an experimental process, right? Where you keep going back and forth through development of features, developing of models, and then coming back and seeing if the results have improved. And typically, too, and this is kind of more of a meta concept for everyone, is that it has to be, in order for it to work, at least where I've seen it outside of research context where we do these kind of one-offs, it really has to be embedded in kind of normal practices, right? So if you have like this fringe organization inside your company that's trying to apply machine learning, it typically won't work, right? So you have to have a culture where it really invests. Maybe that's less important right now for the context, but it is a reality. All right, so let's take a step back here and we'll talk about some more specifics, all right? All right, so we talked about this one. Learning functions need to be mapped to inputs to outputs. All right, so we have to be clear understanding that our data can predict what we want it to predict. You typically need a large amount of data, all right? Much more than you would need for inferential or kind of sample-based statistics, right? Much of the field of statistics was based off kind of small sample sets, right? Small n's. Machine learning is based off large n's. You have to have a significant amount of data, typically for it to work. This one, task number 3, is also related to, or item number 3 is related to item number 1, right? Usually there has to be kind of clear feedback, right? Definable goals and metrics. You have to know what you are going to achieve, all right? And you have to know whether you're getting there or not, okay? So this gets back to kind of understanding your business question and metrics so you can say whether your model is doing what you want it to do and whether it's actually providing the value that you hope that it does, all right? Reasoning and diverse background. This is kind of our philosophical one here. All right. No machine learning process is going to understand like the political dynamics in the South China Sea. Just not going to know that. All right. So it needs to be it has to be fairly simple in all fairness. All right. All right. And then this one may be a little bit more controversial. Why the decision was made does not necessarily need to be clear. All right. So when we think, and I'll explain more about this, but when we think about the way that most machine learning algorithms work. It's not true of all. I've actually made a lot of progress on this, right, in terms of just where, explainable AI, things like that. But still, your neural network might use millions of numerical weights in order to do some type of classification. Unpacking that can be quite difficult, right? So using, machine learning in a space where you have to really understand which variables are contributing and why, not always great. All right. A tolerance for suboptimal solutions. All right. This is true of, I don't know why I put a question mark. This is true of most models. We have to just really understand, what's going on inside our machine learning model. All right. Because typically there's always going to be a certain amount of percentage error that we're going to have. And once we put these in and we empower them for making choices for us, it's just really important to understand where those choices could go wrong. All right. And it should be that doesn't change rapidly over time. All right, there's ways to get around this. All right, you can imagine, the preferences associated with Netflix content, as an example, is changing so quickly. But the way to get around it is just They just retrain their algorithms every 24 hours. They're constantly training and constantly learning, which is very expensive. All right. So, but the idea behind, way that most people use machine learning is that the data that they're going to use wouldn't necessarily be changing incredibly quickly, right? It'd be somewhat stable inputs, right? That way you can also track and see how well it's doing in the real world, right? If that data stream is fairly stable, right? But many times it's not. All right. So those are the conditions, all right? So again, part of this is not to dissuade you that machine learning isn't having a huge impact or AI hasn't a huge impact. It has, right? It definitely has. But I think people approach it just as a one-size-fits-all type of solution. It's really not that, okay? It's really, there has to be these conditions, at least in an ideal world. Now, some of them can be bent. This is the matrix. Rules can be broken. But those are the ones that make for the conditions to be ideal, right, for this to work, all right? Okay, so let's just talk about how machines do this learning. How does it happen? All right, there's break down to like 3 high-level parts. This is an oversimplification, but has the benefit of being true. All right, so we have our data input. All right, we have a level of abstraction of that data. All right, and then we have a generalization of that abstraction. All right, so this is past data. All right, so going back to the beginning here, data input. All right, it's information that can be utilized as a basis for future decision making. All right, so put that in the context of the other criteria. Inputs have to match to outputs. All right, that this is the data that we can use to predict in the future. All right, most of machine learning, if not all of machine learning, is dedicated towards prediction. Right, we want to figure out what's going on in the future. All right, so this input data that we have that we know could potentially, right, should potentially be able to predict kind of some event in the future is represented in a broader way, right, using an algorithm. All right. So we have it down here in kind of the weeds, you can think about it, and then the algorithm kind of pulls it up in a broader way, all right, and develops a memory about it, right? Understands the patterns, learns the patterns, and then this is generalized. Oops. Whoa. All right. And then the abstracted representation is generalized to form a framework of decision making. All right. So that just means like when new data comes in, all right, whatever that model that has been learned, right, this model, right, can then be generalized to make predictions. Right. So just regardless of what's happened in the past, that training data is learned, the new data comes in, we use that past information to kind of generalize about what we're going to do in the future. This is just a terrible, like a copy and paste from that same book that I referenced above. But we think about our data here, right? This is the process of developing and gathering and putting the data. This is the machine learning development process, right? And this is putting it into deployment, right? This is not that different than any other type of model, all right? We just have to say to ourselves, what level of abstraction and generalization do we accept, or what is the risk associated with the type of question that we're asking, all right? Because it could be that we just abstract too far away, right? And that when we go to generalize it to new data, we have really big error terms, right? So there's a balance here. And let me just re-articulate, all right, the kind of 3-phase process, all right? So here, when we think about kind of this very high-level data, abstraction and generalization, we think about kind of this is our data process, right? We're gathering and acquiring the data, all right? And then in these 2 phases, right, we're kind of generalizing for the most part, right? Or I'm sorry, we're doing kind of abstraction, right? All right, we're taking that data and we're trying to fit it into a model that then can be used for new data for generalization, which is when we put it out into the world, right? And then expose it to new data that it hasn't seen yet. Sorry. Okay, so let's get into terms and phrases, all right? Methods and terms. That's very high level, all right? So, to encapsulate all this, the way that we're going to approach the class to get you guys immersed into what is machine learning is to work through terms and phrases and concepts in each one of these phases of the machine learning process, all right? And this idea development, this data prep and exploration, and solution development. All right, so we're going to work through, and each over the next 3 weeks, we're going to focus on terms and concepts from each one of these steps along the way. All right. So some of the first ones here that we're going to dive into is idea development. In the idea development category, well, anyway, you can read them here. I'm going to go through each one of these in detail. And then the next phase, we're going to do data prep and problem exploration, and then finally solution development. Right? And then for the rest of the semester, we're going to take all these concepts and put them all together and learn several different models. But before which, by working through these, we should have a solid foundation in exactly what we're talking about. We'll be able to speak the same language of machine learning, and then we'll move forward. All right? Okay, so I'm going to stop right there, and I'm going to do a separate little video because this one's already going pretty long. I'm going to do a separate video for phase 1. All right, so this is 25 minutes here, but this is a very high-level overview of machine learning generally. All right, and we'll get into more details about what some of these terms mean as it relates to machine learning in phase 1.